This video is to show you 3 additional example problems of tabular integration by parts. There is another video that shows you when to use integration by parts, why it works, and how to use it. I will give you just briefly that we use tabular integration by parts when u is equal to a polynomial. And it's especially useful when u is equal to a polynomial that is degree 2 or higher. It works for degree 1 as well, but it's especially useful in the case where it's degree 2 or higher because it saves you some work. If you want to see where the formula comes from and why where the method comes from and why we use it, I recommend that you watch that other video instead. This is just going to be some hard and fast practice with tabular integration by parts, just so that you can get the hang of it by seeing more examples. So here's our first example. Let's make it particularly involved. So let's say we've got this 5th degree polynomial times, let's say, cosine of 2x. All right, so I notice that basic rules do not apply because I've got a product. U substitution doesn't apply. If U substitution did apply, I would use u equals 2x. The derivative of 2x is just a 2. It's not this 5th degree polynomial. So u substitution doesn't work. So I'm going to go straight to integration by parts, and because I've got a 5th degree polynomial, I'm going to use the tabular method. As we discussed in the last video, if this is a 5th degree polynomial, I'd have to use traditional integration by parts 5 times in order to get the correct answer. That's a lot of work. We're trying to be efficient in getting our answers, so we're going to use the tabular integration method instead. So we're going to put u over here. I'm going to leave a big space because these derivatives get kind of large. And then put dv over here. Usually we ignore the dx when we do tabular integration. And then you want to differentiate in this column until you get 0. And you want to anti-differentiate in this column until you have the same number of rows in both columns. So first I'm going to differentiate until I get 0. So I have 5x to the 4th minus 6x plus 6, and then differentiate again, and then differentiate again, and then differentiate again, and then again, and then again. Yeah, that's going to be a lot of calculation the traditional way. I'm glad we're doing it this way instead. And for antiderivatives, the antiderivative of cosine is sine. If you've got a kx inside, don't forget to divide by the k. The antiderivative of sine is negative cosine. I've got to divide by the k again, or multiply by 1/2 again. 1/2 times 1/2 is going to give me 1/4. So that's 1, 2, 3 rows. Antiderivative of cosine is sine. We need to multiply by 1/2 again. Antiderivative of negative sine is positive cosine. Multiply by 1/2 again. So I've got 1, 2, 3, 4, 5, I need 6 and 7 rows. Antiderivative of cosine is sine. Multiply by 1/2. Antiderivative of sine is negative cosine. Now, a lot of students are a little bit unsure of their SIGN sign conventions with antiderivatives. I think most people remember that the derivative of sine is positive cosine and the derivative of cosine is negative. So you can use that to check. After I've done something like this with integration by parts and I'm anti-differentiating, and maybe I'm a little bit more unsure of my antiderivatives than my derivatives, I always just differentiate back up. Derivative of a negative cosine is a negative times a negative. It's going to be a positive sign. Derivative of sine is cosine. Derivative of cosine is negative sine. Good. Derivative of negative sine is negative cosine. Derivative of negative cosine is positive sine. Derivative of sine is cosine. So that's all good. And then if I keep multiplying these by 2, 1 over 64 times 2 is 1 over 32. That times 2 is 1 over 16. That times 2 is 1 over 8. That times 2 is 1 over 4. That times 2 is 1/2. And that times 2 is 1. Yes. So we know we did it right. Now, for the sign convention for tabular integration, remember we start with a positive number, then negative, positive, then negative, then positive, then negative, then positive. And you are multiplying across diagonals. Make sure if you've got multiple terms like we do here, you include parentheses as a grouping symbol. You want to multiply and then multiply by positive 1. So we get 1/2 x to the 5th minus 3x squared plus 6x times sine of 2x. And then you want to multiply across this diagonal. That times that is going to give me a negative 1/4 times that polynomial. Times a negative 1, negative times a negative is going to make that positive. Then multiply across this diagonal, and you're adding that result. And I like to put the polynomial after that coefficient and then the trig function on the end. That's just convention. It just makes it look a little cleaner. That times a positive 1, so I'm keeping that negative sign that was already there. Then I multiply these two guys. So I've got 60 over 16 times x squared times cosine, and that's multiplied by a negative 1. And then I multiply these two guys, and multiply by positive 1. And then multiply these two guys. Negative times a negative is positive. So that's my answer. It's just not simplified. We multiply by positive 1, and add. Multiply and add. Multiply and add. Multiply and add. Multiply and add. And multiply and add. And every time make sure you keep that sign convention. So maybe I should say it differently. Multiply, keep the sign, then add. Multiply, change the sign, then add. Multiply, keep the sign, then add. Multiply, change the sign, and then add. Multiply, keep the sign, and then add. Multiply, change the sign, and then add. So this is our answer. It's not simplified. Clearly, 60 can be divided by 2. We get 30. 16 divided by 2 is 8. 30 divided by 2 is 15. And 8 divided by 2 is 4. So that should be 15 over 4. And then over here, let's see. If I divide this by 4, I get 30. If I divide this by 4, I get 8. Divide that by 2, I get 15. Divide that by 2, I get 4. So I get a 15 over 4 again. Over here, I've got, let's divide by 4. I get 30. Divide by 4, I get 16. Divide by 2, I get 15. Divide by 2, I get 8. Okay, so this is our final answer. 1/2. Now, if you prefer, you could collect like terms, but I am not going to ask my students to collect like terms on a problem like this on a test. Not because it's difficult. I think we all know how to distribute and simplify polynomial expressions. But I just don't want you to waste time on a Calculus 2 test doing elementary algebra unless it's actually necessary and relevant and helpful to the calculus that we're trying to do. All right. But leaving unsimplified coefficients, that really bothers me. So it's just a personal choice. That's our final answer. And that's our first example of tabular. Now here's an example where you might not use tabular, you might not need to, but it's quicker this way. You've got 2x minus 1 times, let's say, e to the 3x. You could just use traditional integration by parts, that'd be fine, that's your u and that's your dv, but look how much simpler it is with tabular. U goes here, dv goes there. Use the polynomial. Take the derivative until you get 0. dv is the exponential. Anti-differentiate until you catch up with the 0. Dividing by that 3 every time, or multiplying by 1/3, same thing. Now multiply across the diagonals. And then add, then multiply, change the sign, and then add, and you're done. You could simplify that as well, but you don't have to. All right. Let's do one more. Oops. We just did cosine and an exponential. I think I want to do another trig function. Let's do sine. X over 3. All right. So I notice basic rules do not apply. U sub does not apply. So integration by parts is the way to go. Excuse me. We want u to be our polynomial, dv is everything else. Now since u is a 4th degree polynomial, tabular is going to be the way to go. It's simpler and faster than doing integration by parts 4 times. So u goes here. And we're going to differentiate until we get 0. Oops, I didn't get 0 yet, did I? There we go. And then for sine of x over 3, anti-differentiate. Antiderivative of sine is negative cosine. We're dividing by 1/3, so that's multiplying by 3. Antiderivative of negative cosine is negative sine. Multiply by 3 again. Antiderivative of negative sine is cosine. Antiderivative of cosine is sine. Antiderivative of sine is negative cosine. And 3 times 81, that's 243. All right. Don't forget your sign convention, SIGN sign convention over here. Plus, minus, plus, minus, plus, minus. Always start with plus. Use parentheses as grouping symbols. You're going to multiply, keep the sign, and add. Multiply, change the sign, and add. Multiply, keep the sign, and add. Multiply, change the sign, and add. Multiply, keep the sign, and add. And then don't forget your plus c. So let's write it down. Multiply. keep the sign. It was negative, we're just going to keep it negative. And then add, multiply. Change the sign. Negative times a negative is going to make that a positive. And add, multiply. Keep the sign and add, multiply. And add. Or that's multiply, change the sign and add, and then multiply. I don't know what 24 times 243 is off the top of my head. And add plus C. Alright guys, so that's how you do it, and I would clean up that coefficient. I'm not going to do the arithmetic right now in the video. So we're done. That's tabular integration by parts.